One of the most famous and romantic stories in number theory is the legendary tale known as Fermat's last theorem. While in the previous lecture we saw that there exist natural number solutions to the Pythagorean equation x squared plus y squared equals z squared, Fermat asserted in 1637 that for any fixed natural number exponent n greater than 2, there are no natural number solutions x, y, and z to the equation x to the n power plus y to the n power equals z to the n power. Fermat penned this assertion in the margin of his copy of Dauphintus's text entitled Arithmetica, along with a cryptic and now infamous reference to its proof. After highlighting the history of this most celebrated equation in mathematics, we'll verify that to establish Fermat's claim, we need only prove that his equation has no solutions for exponents equal to 4 and equal to each prime number beyond 2. In fact, we'll discuss how Fermat himself proved the equation has no solutions when the exponent equals 4 using his ingenious method of descent, an idea that beautifully mirrors his method of ascent described in the previous lecture. There's a long and impressive list of great mathematicians who've made progress towards resolving Fermat's last theorem. Here we'll celebrate and highlight some of the contributions made by Leonhard Euler, Sophie Germain, Johann Dirichlet, and Adrien-Marie Legendre in the late 18th century. In the next century, Gabriel Lemay produced what he believed to be a correct and complete proof of Fermat's last theorem. However, Ernst Kummer quickly discovered a subtle error in the argument. Kummer's attempt to repair the problem led to an entirely new field of study, now known as algebraic number theory. Thus, we see that while none of these great 18th and 19th century minds produced a complete solution to this challenging conundrum of Fermat, they did move the frontiers of number theory forward with their creativity, imagination, and profound insights. A complete proof of Fermat's famous theorem, however, would have to wait until the end of the 20th century. We'll have to wait as well for this dramatic story to conclude in Lecture 18. Well, I want to open this lecture with the story of Fermat and his many so-called theorems. Recall that Pierre de Fermat was a 17th century French lawyer who was also actually a member of the local parliament in Toulouse. Number theory was a leisure activity to Fermat. He was indeed a gentleman scholar who was sometimes somewhat reclusive and secretive in his work. Since Fermat viewed his passion toward number theory as recreation, he wouldn't publish his results in scholarly journals and felt no obligation to write complete and correct proofs of his mathematical assertions. This wasn't his business, this was his pleasure. Instead, he'd write notes in the margins of books and describe his mathematical discoveries in letters to mathematicians of the day. Despite his lack of formal rigor, his insights were remarkable, and his contributions to mathematics enormous. Given his extraordinary mathematical creativity and originality, the mathematics community has turned a blind eye to his cavalier treatment of the rigors of proof. Other mathematicians that followed Fermat either produced counterexamples to those assertions that were not true in general, or provided mathematical proofs to those assertions of Fermat that were in fact theorems and for which Fermat himself did not prove. Over 300 years later, all of Fermat's assertions were resolved one way or another. All, that is, but one last assertion. Because it was the last assertion that remained open, it became known as Fermat's last theorem. And it is the story of this assertion that we will now tell. Fermat studied the Latin translation of Dauphintus's Arithmetica with great care and much interest. In fact, he made many notes in the margins of his copy. Question 2.8 in Arithmetica asked how to express a given square natural number as the sum of two other square natural numbers. In other words, the Pythagorean equation x squared plus y squared equals z squared. We'll actually study this equation for ourselves in lecture 16. Well, it was this question of Dauphintus that, around the year 1640, inspired Fermat to write down the most famous Dauphintine equation in number theory. In his copy of Arithmetica, Fermat wrote in Latin the most famous marginal note in the history of mathematics. Translated, he wrote, "It is impossible to separate a cube into two cubes, or a fourth power into two fourth powers, or in general, any power higher than the second into two like powers. I have discovered a truly marvelous proof of this, which this margin is too narrow to contain." Well, we state Fermat's marginal assertion formally as, given any fixed natural number n that's greater than 2, there are no natural numbers x, y, and z that satisfy the Dauphintine equation x to the n plus y to the n equals z to the n. Well, it was this assertion that was the last of all of Fermat's claims to be verified or disproved. Because this was the last to be disposed with, it became known as Fermat's last theorem. Now, to disprove his claim, we need to only find a natural number n that exceeds 2, for which the Dauphintine equation x to the n plus y to the n equals z to the n has natural number solutions. We just have to find a solution. So one counterexample is all that's required. On the other hand, to prove his assertion is true, we need to show that there are no natural number solutions for any exponent n. So Fermat's last theorem is a statement that the Fermat equation has no natural number solutions for any exponent n that exceeds 2. In other words, it is in fact infinitely many statements. A statement for n equals 3, 4, 5, 6, 7, 8, and so on. Namely, we have to prove that no matter what the exponent is, whether it's 3, 4, 5, 6, 7, 8, and so on, that there are no natural number solutions x, y, z to that equation. Well, we now wonder if we really need to prove all these cases in order to establish his assertion. To resolve this puzzle, we first review an important property of exponents that we saw long ago in our school math days. Specifically, we noticed that x to the 6th power just means x multiplied by itself 6 times, x times x times x times x times x times x, which if we group them just in pairs, we'd see x squared times x squared times x squared. So we'd have 3 of them, which would be x squared cubed. In other words, we see that x to the 6th equals x squared all cubed. Well, more generally, if a natural number n can be factored as n, let's say, equals a times b, then x to the n equals x to the a all raised to the b. Using this property, we claim that to prove Fermat's last theorem for any exponent n greater than 2, it's enough to just prove Fermat's last theorem for the case in which n equals 4 and n equals an odd prime number, 3, 5, 7, 11, 13, and so forth. In other words, there's no need to check any other composite exponents other than 4. This claim would certainly reduce the number of exponents to check, because we only have to check all the odd primes and the number 4. Now, why is this claim true? Well, let's now suppose that we've already established Fermat's last theorem for all odd prime exponents and the exponent 4. So we're going to assume that. That means any odd exponent at all and the exponent 4, when we look at Fermat's equation, there are no natural number solutions. So what do we do from here? Well, we now consider a composite exponent greater than 2. That's not 4. So for example, let's consider n equals 6. If we now assume, contrary to what we want, that there is a natural number solution to x to the 6th plus y to the 6th equals z to the 6th, then by our property of exponents, we can rewrite this as the equivalent equation x squared cubed plus y squared cubed equals z squared cubed. Now, because x, y, and z are natural numbers, so are their squares. In other words, we've just found a natural number solution to Fermat's equation with n equals 3, an odd prime, right? Because I have x squared cubed plus y squared cubed equals z squared cubed. So we have a natural number solution. But this contradicts our hypothesis that there were no such solutions when we had the exponent equal to the prime 3. Therefore, we must have no natural number solutions for the exponent 6 as well. Because if we had a solution when the exponent is 6, that would automatically imply a solution when exponent equals 6. That would imply a solution when the exponent was 3, which we're assuming, in fact, does not exist. There are no solutions in that case. Well, let's now suppose that we consider the exponent now 8. So if we assume that there is a natural number solution to x to the 8th plus y to the 8th equals z to the 8th, then again, by our property of exponents, we could rewrite this as the equivalent equation x squared to the 4th power plus y squared to the 4th power equals z squared to the 4th power, which again yields a contradiction since there are no natural number solutions with an exponent of 4. Hence, there cannot be natural number solutions for the exponent 8. Well, this argument can be applied for all composite number exponents greater than 2. So if we have a composite natural number greater than 2, then either it must be an odd number and have an odd prime factor in it, or if there are no odd primes in all, then in fact it must have a factor of 4 at the very least. And in either case, by our hypothesis, the result holds for 4 and for all the odd primes. We therefore conclude that Fermat's last theorem must also hold for all natural number exponents greater than 2. In other words, this line of reasoning establishes the fact that it's enough to consider just the special exponents 4 and all the odd primes. Still a tall order, still infinitely many different cases to check. But you can see that we've gotten actually rid of infinitely many cases that would follow automatically from just knowing these cases. And so the mathematics community now turns to these cases and forgets about exponents of 8 and 6 because they would follow from these cases. Well, Fermat himself devised an ingenious method to prove that his equation has no natural number solutions for the exponent 4. He called this process the method of descent. And in fact, it mirrors his method of ascent, which we described in the previous lecture. In Fermat's method of descent, we assume that we have a natural number solution to a Diophantine equation, not necessarily x to the n plus y to the n equals z to the n. His method actually can be applied to even a broader collection of equations. Now, using this assumed solution, we construct a smaller natural number solution Now, if we could do that, we could then repeat the process again with this smaller solution. Now, for example, let me just give you a sense of what's going on here. Suppose we have an equation, some equation out there, and we assume that 101 is a solution. Let's now further suppose that we could actually use this alleged solution of 101 to produce another natural number solution that is smaller, perhaps just for fun, say 91. So 91 is now a solution which we derived from the first solution, 101. Well, now with this new smaller solution, 91, we could repeat the exact same process to find a still smaller natural number solution, let's say 81. Well, repeating this process indefinitely, we would create an arbitrarily long chain of natural numbers that are getting smaller and smaller. Well, there's a problem though, because there are only finitely many natural numbers smaller than any given number. For example, 101, there's only 101 numbers between the smallest natural number 1 and 101. So there's only 100 numbers smaller than 101 that are natural numbers. So in our example, using, let's say, 81, the number we have last, I could generate another natural number solution, perhaps 71, then 61, then 51, then 41, then 31, then 21, then 11, and then I get to 1. Now, here we can't go any lower since there are no natural numbers smaller than 1. 1's the first natural number. However, the general method asserts that given any natural number solution, we can use it to produce another smaller natural number solution. Well, this conclusion actually leads to a contradiction, and thus our assumption that a first such natural number solution existed must be false. Hence, there are no natural number solutions to the original Diophantine equation. Now, we again see a divide and conquer theme in Fermat's method of descent. Now, let me just say a word of comparison here. Remember, Fermat's method of ascent was one in which we first start with a solution that we know is true, and then we use it to build bigger and bigger and bigger ones, and we can repeat that forever so we get infinitely many solutions. Contrary, the method of descent, we assume we have a solution, and then we build a smaller natural number solution, and that process can be repeated forever, but that's a contradiction since we hit rock bottom at some point. Therefore, there are no solutions here. Well, this method turns out to be extremely useful and can be applied in a variety of mathematical contexts. Fermat himself, in fact, wrote about his method. As ordinary methods, such as are found in books, are inadequate to proving such difficult propositions, I discovered at last a most singular method, which I called the infinite descent. So you could tell even Fermat realized the import of his method. Well, Fermat applied this method in an extremely clever way to a Diophantine equation that is very similar to his famous one. He was able to prove that there are no natural number solutions to the Diophantine equation x to the fourth plus y to the fourth equals z squared. Notice that now it's a z squared, not a z to the fourth, as you might have expected. Well, he proved that there are no natural number solutions to that equation, and using this result, we ourselves are able to show that there are no solutions to the equation x to the fourth plus y to the fourth equals z to the fourth. Why? Well, let's assume that there were natural number solutions to the equation x to the fourth plus y to the fourth equals z to the fourth. Well, then we could write the solution as x to the fourth plus y to the fourth equals z squared all squared. And now, in other words, we see that we just found a solution x, y, and z squared to the equation x to the fourth plus y to the fourth equals z squared, which Fermat showed didn't exist. Hence, there must in fact be no natural number solutions to Fermat's original equation with the exponent 4. And Fermat himself gave a complete proof in this special case. And by the way, let me just say off the record here that many people believe that this exact method, the method of descent, was the method that Fermat had in his mind that he believed would work for other powers beyond 4. And that's why he wrote this wonderful thing. I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. The idea being that, okay, I did it for the exponent 4, and blah, 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 it'll work for the other powers as well. And I believe that this is in fact what Fermat thought. It turns out, however, that no one's been able to find a proof for the higher powers using this particular ingenious method that works for the exponent 4. So, given Fermat's work, we need only prove Fermat's last theorem is true for each odd prime exponent, which is still a tall order indeed. Well, we now turn to some highlights of the 18th and 19th century struggle to find a proof of Fermat's last theorem. Now, after Fermat, Leonhard Euler was the next to make serious progress on this question. Now, he was able to adopt Fermat's own method of descent in a very delicate manner to prove that Fermat's equation had no natural number solutions for n equals 3. So we can cross off the exponent 3 from our list of our to-do list, if you will. Well, there were, in fact, some small errors and gaps in Euler's work, but those were all easy to repair, in fact, by applying results due to Euler himself. His proof actually generated a good bit of interest in the original question, and in some sense, it was Euler who got the math community excited about this particular challenge of Fermat's. Next, we move to the groundbreaking work of Sophie Germain. Sophie Germain, born on April 1, 1776, was inspired to become a mathematician when at the age of 13, she read about Archimedes. Early on, she would actually submit papers and write letters under the pseudonym Monsieur Leblanc. After Gauss, one of her supporters, discovered that Monsieur Leblanc was in fact a female author, he actually wrote about her and her work. When a person of the sex which, according to our customs and prejudices, must encounter infinitely more difficulties than men to familiarize herself with these thorny researches, succeeds nonetheless in surmounting these obstacles and penetrating the most obscure parts of them, then without doubt she must have the noblest courage, quite extraordinary talents, and superior genius. So you could see Gauss held Sophie Germain in great regard and respect. Well, in fact, she produced a number of extremely important results in number theory. In fact, one of them led to the concept of what are now called Germain primes. A prime number p is a Germain prime if the number 2p plus 1 is also prime. So, for example, 3 is a Germain prime, since 3 is prime, and 2 times 3 plus 1 is 7, and that's also a prime. However, the number 7, which is a prime, is not a Germain prime, because 2 times 7 plus 1 is 15, and 15 is, of course, not a prime number. Well, one of Germain's most significant discoveries was connected with Fermat's last theorem. She proved a very deep theorem that asserts that if x, y, and z are natural numbers that satisfy the equation x to the 5th plus y to the 5th equals z to the 5th, then the number 5 must be a factor of either the x, the y, or the z. Now you might say, well, gee, that seems like a very specialized theorem. So why was this result so important? Well, in 1825, Dirichlet and Legendre used this result of Germain and generalized the arguments of Euler to establish the truth of Fermat's last theorem for the exponent 5. So we can cross off the next prime, 5, from our to-do list of exponents. 15 years later, in 1839, French mathematician Gabriel Lamé offered a very lengthy proof of Fermat's last theorem for the prime exponent 7, which is the next prime on our list. So we're making a little bit of progress, still have infinitely many more primes ahead. His argument was so complicated that it did not appear at all that it could be extended to any other primes. So it seemed like that was the end of the road for this idea. However, later in 1839, Lemay made an even greater announcement. He claimed to have a proof of Fermat's last theorem for all odd primes. In other words, he claimed to have found a complete proof. Well, sadly, despite the fact that his ideas were indeed ingenious, there was an error in his argument. In fact, since that point, there have been literally thousands of false proofs of Fermat's last theorem, authored by both mathematicians and non-experts, that are always submitted annually to journals, and which the journals, of course, reject. It was the German mathematician Ernst Kummer who quickly noticed the subtle error in Lamay's work. Since Lamay's idea was so clever, however, Kummer attempted to patch up the proof. Now, though his work, in fact, did not complete the proof of Fermat's last theorem, it did provide the foundations for an entirely new branch of number theory, now known as algebraic number theory. Now, the details of Lamay's idea and the error that led to Kummer, the error that led Kummer to his important discoveries will be discussed in some depth in the next lecture. Well, but getting back now to our story of Fermat. In 1847, Kummer extended the ideas of Euler, Germain, Dirichlet, Legendre, and others to prove that Fermat's last theorem is true for all so-called regular prime exponents. Now, a regular prime is a prime that satisfies some very complicated algebraic properties, but I won't bother to go into detail here. Let me just say that if we were to consider all the primes less than 100, then it's been shown that all of these primes are regular primes, except for the primes 37, 59, and 67. Thus, from this small amount of evidence, it would appear that most primes are regular primes. In fact, it's conjectured that approximately 61% of all primes are regular primes. However, it remains an open question to determine if there are infinitely many regular primes. So even though we think that more than half of them, almost 2/3 of them, are regular, we can't even prove that they're infinitely many. So Kummer's great work, which shows that, in fact, Fermat's last theorem holds for the regular primes, in fact, isn't very helpful since we don't know much about the regular primes, even if they're infinitely many. Well, in spite of all these great and important contributions from outstanding minds of the 18th and 19th century, a complete proof of Fermat's last theorem would have to wait until the end of the 20th century. In fact, it was Andrew Wiles who in the 1990s finally gave a correct and complete proof of this 350-year-old open question. However, this dramatic conclusion of this epic number theoretic saga will have to wait until lecture 18. For now, we celebrate Fermat, his wonderful contributions to number theory, and his famous last theorem.